In the just a minute. In the previous session, we were starting to talk about the idea of adding two angular momenta quantum mechanically. And so the simple example that we took to illustrate how to do that at a fairly elementary level, because the full analysis of the addition of angular momenta in quantum mechanics gets pretty heavy. Definitely graduate level can involve group theory, representation theory, something called Clebsch-Gordon coefficients. Don't worry about what they are, but it's quite an advanced topic. So at undergrad level, we'll just sort of scratch the surface a bit, give you more or less a taste of what's involved. So again, start classically, give us motivation on how to handle, what's the appropriate operator as usual for the sum of angular momenta. So as usual, let's be inspired by classical mechanics. Now, in classical mechanics, if you have two angular momenta, so these little wiggles here indicate vectors. So angular momentum is a vector. So if you have two, so say one body and another body, so the first body, first thing, particle, whatever, has momentum L1, talking classically, and the second one has momentum L2, we just add them. So it's just vector addition, right? So like adding two arrows. Now, so correspondence principle, let's take the case now we're talking, say, two identical quantum particles, and for the angular momentum, let's talk spin, right? So just hat these and relabel the L for S, because now we're talking spin. So now we'll have S hat, so the total angular momentum, or in this case, total spin, will be S1 hat plus S2 hat, analogous to this. Right? This is classical, this is quantum. Now, I need to clarify a little bit. This operator, it operates on particle 1, and this operator operates on particle 2. So this operator will change the wave functions, the eigenstates, whatever, of particle 1, and similarly this one for particle 2, which is what these two lines are saying. Right? Now we're talking spin, so there are only two eigenstates for each of the particles. So this particle 1 could have a spin eigenstate of up or down. Right? That's it. And similarly for particle 2, it too, spin up, spin down. They're the only two eigenstates that the particle can have. So you'll have four possibilities for the spin up down for the two particles. Now, this has two possibilities up down, this has two possibilities up down. So listed here are the four possibilities, right? So particle 1 has spin up, particle 2 has spin up. So it's 2 by 2. There's four possibilities, right? Just listed here. So the fourth one would be particle 1 spin down, particle 2 spin down, and then all four, right? Now, so they're the four possible spin states of those two particles, you could say, right? Now, as usual, we want to find, now we're talking spin, so angular momentum, we want to find what's the operator for S squared. So in other words, S hat times S hat. So S hat applied twice, right? So S hat squared. And this S here is the total angular momentum, right? So it's this. So this S here is S1 plus S2. Okay? And also find the Z component of the total spin. So this is the Z component of this, right? And from spin theory, elementary angular momentum theory, we know that the Z component and their squared, they commute. These two operators are compatible. Okay, but remember the S here now is now a sum. We're adding angular momentum, adding spins, right? So S1 plus S2. All right. Now this operator operates on particle 1, and this operator operates on particle 2, and these so S1 does not affect, this operator here does not affect particle 2, and vice versa. So that means these two operators can commute, right? They don't have any effect on each other. So what we're trying to do now is we're trying to find an expression for S squared, and we will once we've got the operator. So we know what the operators S1 and S2 are. We know those, but we don't yet know what S is, or S squared. Well, S is this, but what's S squared? So we want to find operators first, and as usual, once we've got the operators, then we can plug the operators into an eigenequation, solve for the eigenfunctions, the eigenvalues, find expectation values, and so forth. All right. So let's try and find an expression that we can use in an eigenequation for S squared. Now this is the total angular momentum, the total spin in this case, S. So you remember we had L squared. L squared was Lx squared plus Ly squared plus Lz squared. Well, so similarly, so S squared is S1 squared. So Sx squared plus Sy squared plus Sz squared. But Sx, the x component of the total spin, right, squared. But Sx is, if you put an x here, and an x here, and an x here, so Sx, total spin, is S1x plus S2x, S1x plus S2x. And Sy, the total spin, is S1y plus S2y, right, all squared, and similarly for the z. Alright, so you've got 3 squares of sums, so you do all the math. So you'll get an S1x squared, and from here an S1y squared, and here from an S1z squared, and similarly an S2x squared, and an S2y squared, and an S2z squared here, right? Plus a few other terms. Now you may be asking, well, why don't you have like S1x, S2x, but then S2x, S1x? Well, you do, but these two commute, right? So you can change the order; it doesn't matter. So that's where you get the 2. So you get this term. Now, what can we do? Now we know how to work with this. Just one particle, the x component squared. So these 6, we know how to do with these, because they're the z component of one particle each. So we know how to manipulate those. We know how to work with them. The problem is this. Well, there are some tricks, mathematical tricks, and I've asked you, homework. You may remember the step-up operator, the plus, so for S plus, and 3 bars by definition. So it's defined as Sx plus I Sy, hat, right? And the step-down operator for